This talk is fun because every now and then you get somebody who gives a talk and you can just tell like their offhand comments are like the insights that you really wanted to find out, and like the little bitty tidbits of things that they say are some of the most insightful things. So when we did our dry run with Marc, he had a whole bunch of things that were like explaining deep details about how the JVM works in particular. And then some of our feedback was, actually, no, that little thing you said right there, that was really insightful. It's just you can tell somebody who deeply knows the material. So I'm excited to get Marc up here to share really about how you can analyze things in the JVM via dynamic analysis. I guarantee you'll probably have questions if you've ever had to do any of this. He's got a lot of stuff to share. So let's round of applause for Marc Schoenefeld.
Hello. My name is Marc Schoenefeld. I'm a little bit jet-lagged, but I hope I don't fall asleep during the talk. Yes, let's start with dynamic analysis of JVM processes. JVM, Java Virtual Machine, so we have one abbreviation already explained. So what are we going to do? Well, I'm Marc. I do research. I did some reverse engineering with Java, so did some stuff with Trojans and hacked more sockets into LimeWire and other stuff. So you can read it up for the total view. Also did some Android, yeah. So agenda, what are we going to talk about? Java, JVM, runtime artifacts, shortcomings of static tools, common development tools, optimization and synergies, reversing use cases, closing sorts, and then moving forward. What can you do afterwards? You heard this all. A brief overview of Java obfuscation methods. So first there was a Java and obfuscation, early Java, simple obfuscation, more advanced obfuscation, countermeasures, strong obfuscation, modern obfuscation. So it's a game to hunt each other. There's a little bit of history. JVM 1995. So there's one class containing code and metadata. Obfuscation required to protect secrets in the plane of size of Java classes. Control flow. Well, you had all this nice instruction where you could confuse the stack and the tools, the dup, swap, dup, pop2. You had identifiers which you could mangle, like with names of methods, with identifiers, put them into RC4, get some nice names, homoglyphs, restricted keywords. You can remove the debug information. There are class loader tricks, XOR class loaders, encrypted class loaders, all this kind of stuff. You can have anti-debugging code like poison, two-string methods, timing checks, rock annotation processing. Essential, you have to know all this. You have to know the platform. You have to know, the platform. You have to know where to find the right things to use or to hook. You have to know the bytecode. There you have to know what the actual code execution does and not what the Java source tells you or the decompiler tells you it's doing. We have one friend with the obfuscation. We have the Java verifier. The Java verifier is the point in the JVM that even highly obfuscated code has to comply to. It has to comply with the Java verifier. It has to sound bytecode. Don't jump outside the method or jump into the middle of instructions. Methods cannot be longer than one page of instructions. Sound metadata, there is a stack balance, there is a stack that is maintained during runtime, and that is cross-checked with metadata in the class, metadata like the stack height, the max height, or the stack map table, difficult, that has been built up by the compiler. So we at least the JVM hopes to know what is on the stack at which point and which slot and which type does it have. Besides that, there's also the enforcement of packages like the old Java, and with Java 9 there was the module visibility being introduced. You may have seen all these nice new commands with add opens and add extends and all these things. You can find that all later in the links that I have here in the slide. So the JVM specification is always your friend when dealing with the details. A short intermission. We are having a few examples with Mixed-boolean arithmetics. So compilers, they differ in the ability to reconstruct simple expression from an arbitrary complicated one. Mixed-boolean expression is an often used technique for obfuscation, and yeah, basically we have a simple expression, and that can be spread out to some complicated ones, and there are some prominent ones, and we are going to visit these. And this is just a simple case that can be used recursively, but sometimes the tools already fail with the first stage. Okay, bytecode. What is bytecode? Here we have our first MBA, and we have a method. Method does a doit. A doit compares the simple version to the MBA version of this XOR. And we add two numbers, and when we have a match, then we have shown for this particular case that these terms are okay. That's our test case here. So this is essentially what we're doing. How does it look in real life? This is just the facade. This is source code. Java does not care about source code. Java cares about bytecode. And here we see what our tool, Java P, that is the disassembler from Java, gets out of this class. We have some constructor, so we can ignore it here. And here was where the meat is. We have the XOR on the left side, and we have the two other instructions on the right side. Put two values on the stack, do the XOR, store it somewhere, do the XOR, do the inclusive OR, and leave it on the stack, do the same, and then do the IAND. And now we subtract it, and we store it. And that is what the JVM, it doesn't optimize anyway. It takes the stuff again from the slot, take this one we have stored here, and then we compare it, and if it's the same, we have a 1, and if not, a bad, we have 0. So, but that's how bytecode works. And where do we find bytecode in classes? We find it in, it goes backwards. We have classes. We have a constant pool, we have interfaces, fields, methods, and other stuff which we won't cover here. And in the constant pools, we have all this, we have all the values, we have the strings, we have the types. And in the methods, we have a code section. In the code section, there is the bytecode. The bytecode is here in the, whoops. Why does it not work? The bytecode is here in the method section. So we have 1 to n methods. There can be a lot of methods because it's a 2-byte counter. And there are the methods. Here are the fields. We can have constants. And every class, according to the Java version, has a version, and Java 8 has a different version than Java 23, for example. It goes upwards, and depending on the version, the verifier does the different checks. That's a detail which might be interesting later, but may not relevant at all, depending on what you're doing. how do you deliver class files? Java class files are delivered via jar files, distributed zip files, 1 to n classes in one jar, and you also have the resources in there, like images or application configuration files, service setups. For us, it's interesting, where does it all start? It starts in the main class tag, and that's a class that's actually directly loaded from the jar. The main class is where the unknown code bootstraps, and that's the less protected point, and where we can easily best hook and then trace from there. So more subtleties, there are certain naming restrictions, for example, for file systems, which don't apply in jar files. You can have native code. The native code can be in the jar, but it has to be dropped into a temp directory. That it's where the stealthiness may go away, and yeah. So you don't find that much native code in unsolicited jars. Yeah, you may want to use a decompiler to get to what is actually going on. But there's a problem. Java, the language is not what is actually done during runtime. The Java source code is transformed into bytecode, which we have seen, which creates difficulties to construct the original logic in some point. Java C, the Java default compiler, more a translator, does not optimize code beyond some constant folding. The compiler in itself is the JIT. We come to that later. That does the real magic. There are limitations. Decompilers that struggle to keep up with new Java versions, sometimes even struggle with old Java versions. Some constructs, lambdas, records, switch expressions. Sometimes they are not shown as intended. There is a source language obfuscation. Java is the default compiler, so the decompilers are focused on, but you may have different, as it's bytecode and bytecode is executed, they come from different sources. So whoever supplied the class file may have choose something different, handmade, or Kotlin, or Scala, or Groovy, whatever you choose can emit different bytecode patterns than Java C, and your decompiler may fail in this case. And decompilers, they can be fooled, like for example with the bit shifts. The JVM handles bit shifts like I shift right and shift left, and unsigned shift right, if I remember correctly, is also valid, and it does take the shift value from the stack. So that can be difficult if it's not a simple constant, if it comes from the stack and it's a computed value, and the decompiler has to include all this computation in the source code. So that could be difficult if it's a repeating pattern. So you have a shift that depends on a shift and depends on a shift and depends on a shift. And yeah, that causes some backtracking in Fernflower, for example. Latest Fernflower git head, and that causes out-of-memory error. And the JVM is perfectly fine with executing that, but the Fernflower here bails out with an out-of-memory error. So bit shifts are a problem. Moving on, we can have type conversion chains that can go wrong. The JVM handles slots, and the slots have types. The types can be changed, and that seems to be difficult for a decompiler to track. So long as there are type conversion operators like float to long or long to double, whatever, and here we have chosen float to long and the inverse long to float, and ergo if we have flip these back and forth and we have an odd number, we have a conversion, and if we have an even number, we have a NOP. Yeah, and the decompiler should just write nothing. But what does Fernflower do? It also ends up with an out of memory error. So if you want to protect your code from decompilation, maybe just put some flat of flow too long before the magic happens. So there are more decompilers like, I don't know how to pronounce this, Procyon, a long sequence of the same here, and the same here. Different strategy, it does not have an out-of-memory error. Different strategy is it throws a stack overflow error. So it seems to build up some recursive stuff, like we see here. It builds up the stack, and the stack is too small to process all these 25,000 conversions. And imagine at 26,000, our method starts. There is where the business logic starts, for example. That will be all optimized away by the JIT later. So even it looks complicated, it does not have any runtime effect if the JVM is hot. So moving on, there are arithmetic no-ops. Like you can have the same with negative operators. Nec is nop. And nec also causes stack overflow error if you have it put. And also decompilers can be fooled. There's another player on the market that is JDIScript, and JDIScript also has some problems with keeping up to date with the stack data. And this is here, for example, we have the swap operation. We have two values on the stack, or many, and the last two can always be swapped with a swap operation. So if you have two swaps behind each other, it's again a nop. JDIScript should just delete it away, but instead it spins the CPU high and the GUI looks up. So here it made it until this point, and here until it did not understand anything anymore, and yeah, it gave up. And this computed for some hours until the battery was dry, was empty. Okay, so if you need that, you can always take JDIScript to drain your battery. Okay. Anticipation when code wants to prevent debugging. We have seen the problems with the decompiler. There can be other things where the code can make our life harder. So it can recognize debuggers. It can launch timers, and if there's too much time between two operations, it may be in a GUI or in a command line interface of the debugger, and if the thresholds are not met, we see that it's a debugger. We can look for, well, that is a typical VM checks, look for suspicious directories. There could be obfuscation in the names we have seen. There could be custom encryption methods, not only in the class loader, but we can have custom encryption. We are not using like the SHA-1 from the VM internal classes. We can write our own SHA-1 in, exchange the tables, and may have our own hash codes, stuff like that, or have our own S boxes. That's what we probably can see and can detect, or what will make detection more difficult. So here we see when we have a rock class, and the rock class, we have here this implementation of toString. toString is when you have an object, you want to print the object as a stringified representation. You gather all your data things together, then you do a concatenation, and then just return a string. That's what the fathers of Java thought you would do with it, but You can also do things like, well, start up a binary or just step out the process. So in the life cycle, in the normal life cycle of malware or a ROC binary, this is never executed, but during the analysis phase, that can be an easy hurdle. So look out for two-string methods. They can be some tar-pitting cause that, especially if it deletes your entire directory, it's probably not nice. You have to start up again. Okay, here we see we are really naive and we load the class. And we load the class and we do a new instance, and then JShell, nice as it is, just wants to give us the new instance as a stringified representation, but what it does, it starts up a process builder and starts up a binary. Here we have some sanitized name, but it could also be a fdisk or whatever you choose. And here, yeah, new instance and triggers the code we just saw. Also, round tripping. Maybe you think Java is a nice language. I take my class, I put it in the decompiler, then I have nice Java, and I compile it back, and then I have the new class, and now my malware is not mal anymore, but that can be a problem because bytecode is a superset of what the Java compiler emits, which can make it a successful round trip via Java compiler, decompiler, an unlikely outcome. For example, bytecode is just one subtle difference, can have multiple methods in one class with an identical name, but different return values. So here we have do something, and here do something returns an int, and we have another method which returns a class, a string. That is totally valid in bytecode, but not in Java. If you do the round trip, if we try that, here we run fernflower on our class, and we are decompiling that, and we try to recompile it. We see that the Java compiler does not like it, and yeah, then we have to think about something different. We are left, and we can't do round trip anymore, and we have to hire an consultant. Okay. So reading error messages as hint to the target version. Java has a 6-month cadence with version updates, and with certain older versions still maintained. You will find information in JEP 3. For example, a common visibility enhancement trick in malware was to modify the modifiers, to manipulate the modifiers field, but that was refactored in JDK 12. So if you analyze your code, if you analyze your malware with a newer Java version and you see that error message, you know that is particularly an older version. It could be Java 8, could be Java 11, but typically, due to the large user base of Java 8, just stick with Java 8. So takeaways when dealing with decompilers and other static analysis. Decompilers try to make sense of what happens. In the end, decompilers just transform patterns. Still, so Java is not what is executed, it's bytecode. So don't trust the decompiler is truly identical to what is expressed by bytecode. So that brings us to the tooling. We have different tooling sections. We have static tooling, we have dynamic tooling. Let's go through each of these and see how they can help us with getting to know what is actually going on in our binaries. So Java P, that's the old disassembler. You can read it. It's don't use it. It's even does not help because it does not really print our constants. So, well, if you have no other tools, it just can show you the bytecode. It can show you some kind of the constant pool, but there are better tools. For example, Asmtools. The Asmtools is like a more chain, a tool chain. There's an assembler, disassembler, JSM and dis, they care about the bytecode. You can write bytecode like the stuff I showed with the decompiler fooling. You disassemble it, then you put in your sequences, and then you recompile, you reassemble it, and you have a new class file, and then you put it into the decompiler and it breaks. So that was the workflow I applied there. That is one tool chain, that is JSM and dis, and the other tool chain that is more concerned about metadata, that is JCoder and JDEC. And here we see the JSM and JDIS. Here we have, we have the class file, and we decompile it, we disassemble it, and we see, and we can reassemble it. So that's a good round-trip tool. If you want to use a round-trip tool, that's one you can use. Here, if you're more interested in hacking the metadata, that's the JDEC. And here we see what we saw in the table before. We have all the different metadata fields. And we have this nice presentation. And here we see the interesting stuff, like line number tables, local variable tables. And what this actually means, you can find in the JVM specification. This is very close to the JVM specification. And therefore, when you use JDEC and JCoder, always have the specification right near where it's being applied. You have the Java debugger. The Java debugger is a command line tool for debugging Java programs. It's a front end for the Java platform debugger architecture, more or less a demo program. It is included with the JDK and allows developers to inspect and control the execution of Java programs. So it can set breakpoints and step and inspect and whatever you expect from a debugger. Not so comfortable, but it works. And it works best when you have debugging information like line numbers and local variables tables. And if your supplier of the class file was nice, he compiled it with -g, and then it's all in the class. Or he messed with the debug information, and all your line numbers are 1 or -1. Yeah. So your mileage may vary. There are certain limitations. There's a step granularity is too coarse-grained for debugging. It's designed for debugging Java code, but if you want to step in bytecode, you have to add more line numbers. For example, adapt the line numbers to the bytecode instruction values. So the JDK the JDK designers did not put too much effort into it, so there is no readline support for that tool. So try to get a hold of the RLWOP tool, and then all of a sudden it becomes very comfortable. Until JDK 7, there was also a free debugger available, JShell. That was nice, but it seemed to be out of maintenance. So check your IDE or just use the RLWOP version. It's just a protocol. You can write your own protocol like IOActive did with the famous JWP Shellifier. So it was written in Python, and when you had an open debug open VM, you could just create a process builders or runtime stuff, yeah. So, and do bad stuff, and you go on Showdown and see what VMs are open on the web and do funny stuff with it. Custom JDI scripting can also automate the boring parts, and you can operate on a higher semantical level. You don't have to step manually, you can write a program for that. So here we see JDB, how JDB is started. We have to start the VM with some information, so it's not something that is out of the box, or when you have a VM started, you have to explicitly enable it. And here we see what is possible. We have initialized it, we set a breakpoint, and we run it, and then we end up in the breakpoint, and then we can step, and we can even print the locals. So try it at home, just for the experience. So that was the manual part. We can also do that as being described as some kind of automated fashion, JDIScript. It's just one example for a class of tools. It enables the researchers to write script. It's a wrapper for JDI to set breakpoints, monitor events, best to compile with JDK8 to avoid a version mix-up surprises, or it uses JDK8 language, so language features, so best to compile with JDK8 compiler. You can find it on GitHub, and yeah, it does some nice, abstracts away some nice things. So for example, you would set breakpoints. You could use nice lambda expressions that would set breakpoints. In string constructors. So when you see, oh, my binary is constructing stuff in strings, we can set a breakpoint, and whatever is passed to the constructor later on, we can then follow on. And here we can also set values. So like, for example, here we set a value if it was set when the field was accessed here. And that is how the program works without the scripting. And here, because we have accessed the field, this line is activated, and then we can override values and maybe go over some checks in the binaries we are analyzing. So that was conventional debugging, conventional automation of debugging. Let's go a little bit more, let's become a little bit more dynamic. We have the Java flight recorder. The Java flight recorder is a JVM component that records events during runtime and allows live or post-termination analysis via the JFR tool, JCommand. The larger brother of the JFR tool is the JDK mission control, which nice heat maps and all this kind of things. It gives insights into file usage, sockets, standard crypto operations. Behavior-wise, we can roughly see what happened in the process, under which circumstances, what was recorded in fields, and we see the stack traces. So there are predefined events, but for reversing, we may require custom event definitions. We have to enable our events in the tracing profiles. So we can inject, for example, classes into our binary. With Asmtools, for example, we can extend it from JDK JFR event, or we spawn a method call from there, and we define fields that collect information that is important on the way, maybe a hash, or an encrypted value, or an encoded value, and we have the stack trace. We can record the current time, so we can later align it on a timeline. And when it's configured, if it's not enabled in the JFR profile, it's ignored. But if it's enabled, it's included in the recorder file and available for later inspection. So for example, here, I have written this event for base 64 encoder. So if I have some malware that does base 64 encoding, and I replace or I hook the malware at this point, I can spawn an event and I can collect the value. So here I have to add this new line because the old JDK version did write a new line at the end, which messed up my checksum, and I spent a half day searching that. So, okay, but we have to start our event with begin, and then we do what we actually want to run, and then we commit the event, and we do the return. So this is where the magic happens. We start the event, and we commit the event, and that is being recorded. That is the configuration file. So we see here we have the base 64 encoder. We have it enabled. So, and then we can start our binary under test. And here we have this crack me, for example, and there's a wrapper, and I've exchanged the base 64 methods in this class by my own hooking functions, which were based on the new JDK classes, so I could use current JDK tools. And yeah, then it wrote me some nice logs, and I could see what actually was done in the code. And I could see that the keygen that I wrote did some reflection. It used a direct method access, and then it called the crack me, and then it called into my function, and I could grab the text that was actually being used in the checksum to build the digest. And the digest was later used for checkup. So you can bring some light into all this highly obfuscated code just by injecting hooks in the right places. So we see we have the source text, we have a timestamp, so we know what happened. And we know where it happened. Yeah. So what had to be done in my original class? So that is a code from the crack me here. So it has a key file, and it used old base 64 encoder. JFR works with JDK 9 and newer, so I couldn't use JDK 8 classes. So I replaced this one with Asmtools. I created a dummy string because it was now a static call. So not to mess around too much with the control flow, I just created a dummy string which I can later pop away. But I kept the message signatures similar, so I could just do the same invoke, but here invoke static instead of a virtual because I had no object. It was just a factory method. Okay, that is how that worked. Binary rewriting is nice, but it would even be nicer if binary rewriting worked on yeah, on the fly. So that's what you do with agents. And then you write transformation code that is based on the Java instrumentation package. So that is done with ASM or another appropriate library. The JAgent is bundled in a jar file. Agent calls into the pre-main method, not the main method, the pre-main method here, the pre-main class, and then delegates to an instead of ClassFile transformer. An agent can be detected during runtime, but and it can even be disabled. So again, you need to find out if this happens, and then you just patch the detection away first. You need to be first, and then the idea was nice, but detected. Okay, what is behind all this agent stuff? There is bytecode transformation. Bytecode transformation, not manually with Asmtool, but with libraries that do that on an object model. So it's used for enhancing performance, injecting code, creating proxies. So often you follow the visitor pattern. You visit the class, you visit the methods, you visit the code chunk, and it goes up into this tree, like as we have seen in the diagram, in this tree-like hierarchy. So here we go in the class method visitor, and we go through the bytecode, and each of these elements has an accept function and the method. And that's where you define what will be changed. There are different flavors of bytecode transformation. Here's BCLL. Short, don't use it. It's a legacy. I used it for my Black Hat talk 20 years ago. So currently we would use ASM. ASM is in a lot of, it's well maintained. It's also old. But it's good to know how it works because it's used in many products. The new player on the field is the Java ClassFile API, which is introduced with JDK 20, was introduced with 22, but it is a preview currently. It will be a regular feature with JDK 24. It's developed to address the chicken and egg problem. So you don't have to use newer bytecode libraries. So currently with ASM, you have to wait for the new ASM version because they have they support the new ClassFile version, and with the ClassFile API, you don't have all these dependencies anymore because it's all in one JDK. So it resides in the Java lang ClassFile package, and it's a preview, and it evolves alongside the libraries. So what are typical operations with bytecode transformation libraries? It's modification, transformation, and analysis. You do rewriting, you can insert code. Like here, for example, here we log array creations, we can hook the new array opcode. So here we have some kind of parsing code, what we get. As parameters, we get a size and a type. When we hook the opcode, we get a size and a type, and we can nicely print it. So here we have a test program, and that is what's happening in the bytecode. 10 ints, 5 doubles, and 15 characters. 10 ints, 5 doubles, and 15 characters. 3 arrays created. So that is what's happening without the agent, and with the agent we can nicely hook the opcode, and we can see we have ints, we have doubles, we have the sizes. So if you have these values, and you can think a little bit further, you can find candidates for S boxes or initial IVs, whatever. That's where you can then do this stack trace and see where these elements are created. Just use agent to dig deeper in this in your unknown binary, and it becomes known. So that is what is done here. We can do more. We can modify class files to pre-compute values or AOT neutralize obfuscation. So there may be RC4 obfuscation, and we can just transform it away with an agent or with a program in beforehand. So, or you have a software that uses method handle, and you can remove the method handle and use the original method calls instead. So here, like we have seen before, we could replace, we could write a bytecode transformation that uses one old API and replaces that with a new API or with a hooked API. And here we see how that works. We see we are encountering a virtual invoke virtual instruction. We check is that the right class and is it the right method. And if so, we need to, we know because we coded it that way that we have to swap away the string which is currently, we have to swap what is on the stack and reverse that. Then we have to pop the string away, and then we are again fine with the stack balance. And here we have to create this, we have to create the string instead of the base 64 encoder, because this stand-in allows us microsurgery and leaves the method control flow as is. Yeah, there will be code on GitHub later, and you can just follow up in more time to see what's actually going on. Yeah, and in the end, there's also the new object instruction where this is created. So you see, you just do a nice switch statement, and then you have repurposed the entire class. And what you can also do is analysis. So we can do, we have seen Java P. Java P has problems with printing strings, but sometimes it's very crucial to see, are these two, yeah, here we don't see, are these two spaces, is it one space or three spaces or no space at all? But with the constant pool analyzer tool, for example, which is just a few lines of code, we can extract the values from the constant pool and enhance our Java P output with the exact string contents. So that were agents, that was class file transformation. Now we come to an old relic, the security manager. We can hook resource access with the security manager, and you override checkx function. That has been done a lot of time before. JVM compilation traces. JVM comes with a couple of runtime modes, and you can hook that. You can hook that with a disassemble hook, and there you can see what's going on. So for example, if we run our MBA sample, we see here that we find our instruction again, but it's not optimizing anything away. It could do better if we, for example, use Clang, if we are in the nice situation where we can just translate the stuff. We see that Clang does a better job and just replace our comparison with 1, which is what we expect here. And there's a nice tool which does it all, which we all see. So here on green, on black. If you are a friend of a GUI, you can do that with JITWatch, for example. JITWatch puts it left, middle, right, source, bytecode, assembly code. if you want to dig deeper, that's the tool to go. And yeah, there are subtleties. The JVM does not compile methods that are larger than 8,000 bytecodes, so you may have to enable this don't compile huge methods option, and then you would even compile better the long swap methods, which we have seen. JShell we have seen, we can swap that due to time. Here we have something from pastebin, and we decompile it, and we put it into JShell, and we can see that it's doing some stuff from Dropbox. Or here that we have empty class files which are overwritten, and you can import JDK tools into JShell. This is also nice. What we can also do is also some nice gem. We can find traces in the heap in heap dumps. So often it's not the code which is interesting, it's the data that is on the stack. And for deeper forensic insight we can just look into the objects. And you make a complete heap dump, not just the live objects, because of this they are not reachable, and so it's not included per default, but use all of them. Tune your GC that it's have large RAM, so less GC. The data is longer in the RAM, create a heap dump. Then have a shutdown hook. You can write a shutdown hook. So here I wrapped my keygen with a shutdown hook, so I could look inside what is actually created as strings in the hackme, for example. So this is how a shutdown hook looks. So then when the VM shuts down, here I call into JMX, and JMX calls J's command and J command with a full heap dump, and then it writes the heap dump with the current PID to the file system. And now comes the trick. I can use that heap dump after the process is down, and then I can query all the values in the dumped heap with some query language. For example, I know that all my interesting string starts with helper. Let's just keep that example. And here I can then, like an SQL, like OQL, they call it, I can do a query. And then I see that here my nice digest is printed, and I can find it also in the heap dump. So maybe just the gem is not in the code, it's in the data. So coming to the finale. Final thoughts, decompilers have their blind spots, don't rely on them, verifiable. The verifier is your friend, classes are verifiable, bytecodes, you can recover debug information from metadata is always in class files. You could also regenerate interesting data for instruction level stepping in JDB, or also access data on the stack. So that is up to you to as an exercise after this talk. Moving forward, so the last source code problem won't go away. Recovery skills are essential. Java is not the only language on the JVM playing field. There's Kotlin, Scala. So ramp out on bytecode, read code, play with Asmtools, avoid decompilers for a while, read source code and bytecode side by side. There's a nice tool from ASM which just processes class file into programs. Get familiar with the suspect class, the hook, strings, integers, big integers, string builders. The code in this presentation will be shared on an upcoming GitHub repo, and for updates, just follow me on LinkedIn. Slides will probably be online, and then thank you, and open for Q&A.
Thank you, Marc. All right, we have time for just a question or two before we get a nice 30-minute break. I'll get some food and coffee. Anybody? Marc can ask Marc a question.
Hey there. I was just asking if you wanted to do something like trace every call that some Java binary is doing, what tool would you recommend? Because you talked about a lot of tools. Like, broadly speaking, what would you go with?
Well, do I want to, well, I could trace, for example, the JVM. Like I could hook the invoke virtual calls. Or I could just put JDI and hook all the method calls. I could do that with JDIScript.
So JDIScript would be then the main tool you'd recommend for that? Like he's asking specifically which tool like would you use versus like JDIScript or
tool I would recommend more scripting with a framework and then script on top of that, and then you can also do some filtering in before. We can have some discussion after this talk to get more into details.
Perfect. Anyone else? All right, we'll go ahead and let everybody enjoy the break. Thank you again, Mark. Appreciate your talk.
Yeah, thank you.